After taking apart Falconry 1, I realized a lot of spare rocket parts that would probably never be used again. That got me thinking, what can I build with all this? So I decided to build a supersonic rocket. But I decided to make a few rules to make this challenge more fun and exciting. Rule 1. We can only use spare parts. So we can't buy new parts or 3D print new parts, we can only use parts we already have. Getting new mandatory items like motors or rail guides is okay, and getting new parts not actually part of the rocket itself is also fine. Rule 2. We can't modify individual parts to our specific needs. This means we can't cut body tubes to size or anything like that. Rule 3. The rocket must have a 24mm diameter. And Rule 4, obviously, the rocket must go supersonic. Make sure to like, comment, and subscribe, and let's get started. First, before I even thought of this challenge, I took apart Falconry 1 and put reusable parts on the rocket shelf. The only part I didn't fully take apart was the fin mount. I felt I still had a use for the fins, I just didn't know what. Next, I found a nose cone. It fits a 24mm tube, and it's from an Estes kit I just took apart for Falconry 1 parts more than a year ago. I never had a use for it until now. Then I took out a body tube to see if the nose cone would fit in. It was a 24mm diameter thick wall tube that's about 15 inches long. I actually found this tube in the kitchen a week before and put it on my rocket shelf. That was when I was like, hey, I can build a rocket out of these scratched parts. And why not make it a supersonic rocket? This was when I started making the rules for the challenge. I started constructing the rocket on the simulator called Open Rocket. It's 100% free and works really well. I also added a shock cord and a streamer. The shock cord is a standard elastic shock cord from the same Estes kit I got the nose cone from. The streamer was a 2x56-inch mylar sheet from Apogee Components. You have to buy streamers from Apogee in packs of 2, so this was just the extra after using the other one from Mock Machine. The stability margin had to be a little higher than normal because supersonic flight is weird. The stability margin is the distance between the center of gravity and the center of pressure divided by the diameter of the rocket. For a non-supersonic rocket, the lowest safe stability margin is usually 1 to 1.5. Since this was a supersonic flight, though, the minimum safe stability margin is 2.25 according to Apogee Components. I decided 2.15 would be fine. Because of this, I initially had a 4-fin rocket to lower the center of pressure, but this also sacrificed some velocity, so I eventually changed to 3 fins and added more nose weight. This ended up increasing velocity by about Mach 0.03 compared to the 4-fin design. The motor I selected was an Enertech F44, which is probably the best 24mm motor for supersonic flight without having level 1 certification or buying a brand new reload casing. The simulated velocity was Mach 1.01, just above the goal. This probably meant the rocket wouldn't go supersonic because the sim assumes perfection, and there's probably a little extra mass not accounted for. This was still pretty good though, considering it was only using scratched parts and was only 24mm in diameter. After this, I realized we probably didn't need that high of a stability margin, since we would at most barely poke through the sound barrier. I decided to remove a little nose weight, which lowered the stability margin but also increased the velocity by a little. I also want to note that the center of gravity location here is a little off because of this transition here that I overrode to no mass, and instead I put the whole mass of the body tube on the actual component. In real life, they'd be the same piece, but I was going to sand the top of the body tube to transition better to the nose cone. The reason I did this was because I had no idea how much the transition itself was going to weigh, and I had no way of really estimating since this was way before I actually started building the rocket. In retrospect, though, I was being a little lazy. Because of this, though, the stability margin in this image is probably closer to around 2.2, so I had a little room to remove some nose weight. I decided a simulated margin of around 1.75 would be safe, so I was able to get the sim to say 1.52, which according to my estimate would be a little over 1.75. It would be safe to consider a definite supersonic flight at Mach 1.05, so that was the target. I was able to stretch it to 1.03, which gives us a much higher chance of reaching supersonic velocity. I still wasn't satisfied though. I was afraid all those assumptions I made and all the guessing and cutting corners would result in a failure. Even if all my assumptions were correct, we'd only barely break through the sound barrier, if at all. Because of this, I switched the body tube to another 24mm tube we had, except this was a thin wall tube that was a few inches longer. The mass of this tube was only 11 grams instead of the 27 grams of the other tube. This greatly increased the velocity to Mach 1.09, and also increased the stability margin since it was longer and moved the center of gravity upwards. The reason I was afraid of using this tube at first was because it was thin wall and therefore weaker to high forces. The sim was saying the rocket would pull over 70 Gs, and I was afraid that would crush it. Unfortunately, there were more problems. The mass of the fins were much greater than I thought they would be. This greatly lowered the stability margin and velocity. After this, I decided again I would sacrifice some stability for velocity, since it would only barely poke through the sound barrier if at all, so I was able to stretch it to Mach 1.04, but with a stability margin of only 1.95. You might be wondering where the launch leg is, since that's usually a big contributor in drag. We used a 29mm flyaway railguide we already had from Mock Machine, and we added a 3D printed adapter since this rocket was smaller in diameter. Flyaway railguides disconnect from the rocket after it leaves the launch rail, which decreases a huge amount of drag. Launch lugs can actually cause up to 30% of a rocket's drag, so the flyaway railguide was essential. 3D printing the adapters doesn't count as breaking the rule where we can't print new parts, because this wasn't actually part of the rocket and was a mandatory part. If we bought a flyaway railguide that was the correct size, we would have to buy a 2-pack for $14. This wasn't worth it since we could just 3D print an adapter. We launched at the club just a little after the Mock Machine flight, and last minute I decided to call the rocket Arrow. The rocket just shoots into the sky and disappears. When it finally came down, we only had a body tube, shock cord, and a streamer. The fins and nose cone were gone. The body tube actually got damaged by the G-forces. As you can see, it's bent here. This challenge was fun. It forced me to be resourceful with what I had and not just rely on 3D printing to make specific parts. It also helped me to get rid of some crap that's just been sitting around. Make sure to like, comment, and subscribe, and we'll see you next time.